Okay, I'm assuming if you're here watching this video that you've at least seen some of my others on the valence shell electron pair repulsion model. So I'm just going to start going through what happens when we have 6 electron groups or pairs around a central atom. That gives us what is called octahedral geometry, which tends to frustrate students because the octa prefix, of course, means 8, but there's 6 electron pairs. So I know that that language is a little frustrating, but we'll talk about why that is once we get to drawing this 3-dimensional shape in 2 dimensions, and I can kind of talk about it in a little more detail. So as with other VSEPR structures, you have n-1 options for molecular geometries given an initial VSEPR geometry. So with 6 electron pairs, I have 5 options. So let's jump into the first one, which is that all of them are atoms, such as sulfur hexafluoride. So if I'm thinking about how many valence electrons I have 6 from my sulfur, and then 6 times my 7 for my fluorine, which gives me 48 electrons total to play around with. So I'm going to attach all of my atoms to my central atom, which again feels kind of funny because we're already breaking the octet rule here by putting all these fluorines in there. But now I've used 2, 4, 6, 8, 10, 12 in my bonds. So that gives me 36 left over to play around with. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So I've used up all of my electrons. I don't have any left over that I need to put on my central atom. So this is what I'm working with. So to analyze this thing, to figure out the geometry, I look at the central atom and I say, well, how many electron groups or pairs are around it? I have 6 atoms and no lone pairs. And this is often confusing for students because there's a zillion lone pairs, right? But the lone pairs are on the outer atoms, not on the central atom. So we're focusing our attention on the central atom when we're looking at geometries. And that gives us 6 electron pairs or 6 electron groups. So that gives us octahedral geometry. So I'm going to draw it like an octahedron. So it kind of looks like, I don't know, I think it looks like a jack, if you ever played jacks when you were a kid. And they all have 90-degree angles. So we're just going to draw it that way. So we have fluorines that are on either end of my sulfur. And if I draw it with this orientation, then these 2 are coming out at you. These 2 are going into the page, so I'll draw it that way. This one's coming out at you. This one's coming out at you. And remember that we use these triangles with kind of the base that gets larger and then the point that gets smaller as it goes back into the page to represent the 3-dimensionality there. So that's my octahedron. Everything is right angles, so there's a right angle here, there's a right angle with this guy, there's a right angle with this guy. They're all right angles, so everything is 90 degrees in my octahedron. In order to kind of see this 3-dimensionality, you can see it in my ball and stick model here, which is kind of useful, I think, visually. But if we're also trying to figure out how to visualize this on a 2-dimensional surface, we really have kind of a base that's square if we use our fluorines, and then if we connect in a pyramidal kind of way my atoms to the points, and the points, then we end up with a shape that has 8 surfaces, right? It's an octahedron, so I have a surface, 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 and then 4 surfaces on the bottom half as well. So kind of 2 pyramids with a square base that are put together, which gives me an 8-sided 3-dimensional structure, hence the octahedral geometry, which makes people crabby kind of in general, again, because we're thinking in terms of electron pairs because we're chemists, but from a geometric sense, that gives an 8-sided shape. So the name of the shape of this thing, or the molecular geometry, is an octahedron. Octahedral VSEPR geometry, it's an octahedron for its molecular geometry. Now let's see what happens, throwing my pen around, let's see what happens when we have 5 atoms instead of all 6 that are bonded. So let's take a look at chlorine pentafluoride. So if we have 7 from everything, then that gives us 42 electrons total. Chlorine is at the center, and I'm going to attach like a starfish, all of my fluorines, which means that I've used up 10 electrons in doing so, 2 in each of my bonds. So I have 32 electrons to play around with in my Lewis structure, so I'm going to put 6 of them on each. 6 on each of my fluorines, and I have 5 fluorines total. That means that I've used up 30 of them in putting a full valence on all of my outer atoms, which leaves me 2 electrons that are going to go on the center here. So when I'm thinking of counting, then I have 5 atoms and 1 lone pair, which again gives me those 6 electron pairs. So I say, well, I have octahedral geometry. And the cool thing about octahedrons, because everything is a 90-degree angle, there's no preference like we see in a trigonal bipyramid to taking one from an axial or an equatorial position, because there are no differences in the angles anywhere. There are no equatorial versus axial positions, right? It's all sort of equilateral, I guess, from the middle guy. So when I get rid of one, it doesn't matter which one I take it from. I'm still just left with this shape. So I'm going to draw it like this. I'm going to draw it like an octahedron with this one in the plane, this guy coming out at you, this one coming out at you, this one going back into my page, as is this one. And then I'm going to have my lone pair here at the bottom. You could have the lone pair at the top, you could have it outside. It doesn't really matter how you draw it. I like drawing it this way because that's the way that it's sitting on my page at the moment. Now, if I'm thinking about this in terms of the geometry, because I always am, because that's sort of the name of the game here, then I still have this kind of square surface. And if I attach all of my lines to that top fluorine there, that top atom, then I still end up with something that looks like a pyramid, but it's not a full octahedron anymore, right? It only has kind of the 5 sides instead of the 8. So we have this shape that is now called a square pyramid. So square because of the base, and pyramid because it comes to the point. So octahedral VSEPR geometry, square pyramid, molecular geometry. Now let's go to 4. So if we get rid of another one, because we have a lone pair, then we end up with a structure that looks like this. Let's look at xenon. So we have 8 from xenon. We have 4 times my 7 here. So that gives me 36 electrons to play around with. Xenon's at the center. I'm going to attach my 4 fluorines. The rules for Lewis dot structure are that we put things at the cardinal directions. Oops, not iron. So we're going to put these at, north, south, east, west. And we're going to, in doing so, use up 8 electrons. So I'm going to have 28 electrons that are left over to play around with. Now I have 6 each on my fluorines, which means that when I put the lone pairs on my fluorines, then I've used up 24 of them, which leaves me 4 left over, which will go on my central atom now. So I'm going to put 2 and 2. The notation on that isn't very important, kind of where you put them. The atoms matter with Lewis dot structures, but when you start to break the octet rule, then you're kind of on your own. It gets a little willy-nilly. So we have 4 atoms, 2 lone pairs. Again, looking at the central atom here, which gives me 6 electron pairs total, which means I have octahedral geometry. So I'm going to draw this like an octahedron. I'm going to put the lone pairs on either side, kind of opposite each other, because that makes sense to me. Because the option would be I take away one of these and then I have kind of whatever this thing is. It kind of looks like one of the seesaw sort of looking things. Or I can do this guy, and this is very symmetrical looking. So I'm going to end up taking away like this. So I kind of take the opposite one from what I looked at before. So I'd have a lone pair coming out here, a lone pair coming out on the opposite side. Nature likes symmetry. So when we're looking at these geometries and predicting how they're going to form, then this is a nice symmetrical sort of pattern with a lone pair coming off of each side like this. So the way that I've drawn this is really like this, where 2 of them are coming out at you, 2 are coming back into the page. So now I have atoms that are all in the same plane, and they're in a square shape, so it is aptly named a square plane. Or we'd say that it has square planar geometry. Either one. Now the last two options are much more rare, and so I'm just going to talk about them in generalities because there aren't a lot of molecules that would exist in this particular way. They get kind of funky because it would mean we'd have a lot of extra electrons, and so I'm just going to talk about them in generalities for the last two. So for 3 bonded atoms, I'd have one thing at the center. So A here represents my central atom. Just a generalized thing. My X's here are going to represent my outer atoms. And then my Y's here are going to represent my lone pairs. So sometimes you'll see this notation if you're trying to come up with a way to show geometries where you have the outer atoms and the lone pairs accounted for in the molecular formula. And I'm making air quotes around the molecular formula here because you wouldn't take into account lone pairs in general. But what we're looking at here is a central atom where I have 3 things and 3 lone pairs. So if I take away one of these, and again, it doesn't matter at this point which one I take away, then I'm left with a molecule that looks like this. So structurally, I would draw it like this. I'm going to put my lone pairs top and bottom, and then maybe a lone pair here. And I'll have this guy coming out. Whatever this guy is, it's an X, X, X. And so the way that I've drawn this is actually like this, for kind of looking at it in the plane. So we have one of them coming out at you, 2 of them going back into the page. And if I look at it kind of from this perspective, or even from this perspective, it might look familiar if you've looked at trigonal bipyramidal geometries. We call the shape of this T-shaped. Again, sort of aptly named. All right, so now we're going to come to 2 atoms. So I could either take one from here, or I could take one from here. And hopefully at this point we've been thinking about geometries enough to say that, well, valence shell electron pair repulsion means they want to spread out as much as physically possible. So I'm going to probably take away this guy and leave me with a structure that has 2 bonded atoms that's going to look like this. So the generalized formula, again, this is kind of rare to have octahedral geometry where you have 2 atoms and 4 lone pairs, which again I'm representing here in this generalized kind of way. So again, here's my central atom, here's my outer atoms, and here's the lone pairs that I have. Just again for clarity, because this is not a real molecule, obviously. So I'd have my central atom here, and I could even draw it like this, where I have the atoms coming on opposite ends, and then I'd have all the lone pairs coming out at you. Now in 3-dimensional structures, for my own personal preference, I like putting the lone pairs on the central atom because that helps to show the geometry of the thing. I don't like to put the lone pairs on the outer atoms, just because I think that muddies the water a little bit. So that's just my personal preference. Different professors have different preferences. When in doubt, you should always put all of the electrons on there that exist on there, just for clarity's sake. But if we look at this, then we can see this is going to be a 180-degree angle. And that means that I really just have a linear molecule, and that's going to be the shape of this thing. So octahedral geometry because I have 6 things around a central atom, but a linear molecule because only 2 of them are atoms and those 4 lone pairs. So we have those options that come from 6 electron pairs. That octahedral geometry gives us 5 different shapes. We have an octahedron, we have the square pyramid, we have a square plane, the T-shape, and then linear molecules.